Electric potential, or voltage, is going to be a little trickier. We don't have an exact analog with the gravitational field and the gravitational force and gravitational potential energy. We're striking out into new territory here. Let's review where we started with electricity. Coulomb's law calculated the electric force between two charges, and again we'll use the capital Q and a little q. We then assumed Q was a small positive test charge. We divided the force by Q, and that's how we came up with the definition for electric field, which is kQ over r squared. We then found the electric potential energy here, U sub E, by taking the work done to move two charges close to each other, and we found electric potential energy. We used a little calculus, well, made reference to it, and we came up with the potential energy is equal to K big Q times little q divided by R. What we're going to do now is we went from force to electric field by dividing out little q. We're going to do the same thing again for potential energy. We will divide out the q, and we will define a new term called electric potential or voltage as potential energy per charge, and that's now going to be kQ, no other q here, just the capital Q, divided by R. V is voltage, and it is measured in volts. Another way to talk about voltage is that it's the electric potential energy per charge, which is how we came up with the definition. And potential energy, all energy is in joules, charge is in coulombs, so 1 volt equals 1 joule per coulomb. To make it a little more understandable, let's take a battery here. Okay, let's say it's a 6-volt battery, and we have a plus side and a minus side. As the electrons are spit out by this battery, the electrons come drifting in this way. They come into the battery, and for every coulomb of charge, each coulomb gets 1 joule of energy. So the electrons coming out this side will each have, every coulomb's worth of electrons will have 1 joule of energy. So they came in here with very little energy. The battery transferred the chemical energy from all the various chemical reactions going on here into electrical energy, and this of course you'll recognize as a circuit. Notice how I have the electrons coming out this way. The direction of conventional current, of course, is this way because it's the direction of positive charges. But every coulomb of charge now has 1 joule of energy, and that is what 1 volt is equal to. Another equation we can get from this definition of voltage or electric potential is, here's our definition. Voltage is potential energy per charge. If I have an external force and it does work on this charge, we know from the work energy equation that you're adding energy to the system. In this case, we're going to talk about increasing the potential energy of the charge. We're not going to worry about it having a velocity at this point, just how have we raised its potential energy. So I'm going to say the work of an external field raises the potential energy, and by multiplying through by Q, I get this equation here. Work is equal to QV. So the work done in moving this charge through a voltage difference, a potential here, would be Q times V. If I have a negative charge, you would have a negative in here, so the work would be negative, would be minus QV.